Today I'd like to cover 5 points. The first is to give a quick overview of some of the main weather-related hazards that affect Australia, and then to briefly turn to the history of one or two of those hazards and look at how they've varied over the past century or more. And then I'd like to just recap on some of the main findings of the Working Group 1 IPCC report that helps us to understand some of the interesting things we see in those records. And then we turn to the future and we'll look at how some of these hazards are going to change in the future in response to further global warming. And finally, I'd like to finish by referring to how some of the risks associated with these increases in hazards can be managed. And so here you see a slide which shows some of the main hazards and some of the ones that I'll talk about today. So they include heat waves. Nothing will come to as much of a surprise to any of you I wouldn't have thought, but heat waves, tropical cyclones and other types of severe weather, extreme rainfall and associated flooding, bushfires and drought, and the list goes on. So here's just one illustration of one particular hazard, and this is a record or a time series of the number of times there were major floods in a 1,500 kilometre strip or coastal strip in southeastern Australia, stemming from near Brisbane through Newcastle, Sydney, down to southern New South Wales. And the time series here goes back to 1860 and comes through to near present. And each of these rods tells you how many of those major floods occurred in this region per year. So you can see that in some years, or one particular year, there were 6 of those major floods, whereas in other years there weren't any major floods whatsoever. So there's an enormous range of variability, and there's also enormous variability from year to year, but also from decade to decade, and even from generation to generation. And that's a feature of all of the hazards that affect Australia. And part of the reason for some of this variability is the El Nino-La Nina cycle. So that in this particular case, we know that La Nina tends to increase the risk or the likelihood of floods in this particular part of the world, and it also increases the death tolls associated with the floods that occur in these years. And that's a common theme, that when we look to the future, that variability is not going to go away. It's going to remain a fundamental feature of how we're going to be impacted over the coming century. But now I'd like to talk to look at a different hazard, and this one is related to heat waves. And it shows a similar sort of thing, but the number of times the Australian area average mean temperature jumped into the top 1% on record. So these are the very, very high values. And this time series again shows the number of days in each year that occurred, back to the early 1900s through to near present. And again, you can see lots of year-to-year variability, lots of decade-to-decade variability. But notice back in the early days, in the early 1900s or mid-1900s, there were very, very few instances where the temperature reached these high values. Whereas when you come to more recent times, it became much, much more common. And in fact, in recent times, we're seeing, in a couple of instances, over 20 days in 1 year where the temperature reached these high levels. So there's clearly something more going on than just natural variability. And so in order to explain that previous slide, let's now recap on some of the main findings of the IPCC report. So the first point is the point that I just made before, and that is that climate variability and long-term trends can arise naturally. You don't need anthropogenic or human-forced climate change to bring that about. But we've seen that globally and in Australia and right around the world, that the surface air temperature has risen over the past century. And we also know that since the beginning of the Industrial Revolution, that humans have caused a very large increase in the concentration in the atmosphere of carbon dioxide and other greenhouse gases. And in fact, the concentrations we have now in the atmosphere are larger than they've been for at least 800,000 years. And these increases in greenhouse gases have reinforced the Earth's greenhouse effect, thereby warming the surface of the planet. And in fact, we know that using modern, sophisticated mathematical models of the Earth's climate system, that the only way those models are able to simulate the observed warming is if they incorporate these anthropogenic increases in greenhouse gases. If you use exactly the same models, but you only force them with natural processes, for example, volcanic eruptions, solar variability, then they exhibit lots of bumps and wiggles, but they don't exhibit that accelerated warming that we've all actually witnessed. And that's responsible for, partially responsible for the picture we saw in the previous slide. So now what I'd like to do is turn to an idealised situation to illustrate one very important point. You often hear about global warming in terms of 1 degree, 2 degrees, 3 degrees and so on. And to be honest, it doesn't sound like very much in terms of human experience at a particular location. But what this shows is an idealised situation where we have a region where there's lots of variability in the temperature at that particular region. And that's exhibited by the black bell curve or normal distribution. So a lot of the time the temperature will vary around about the long-term average, but in some years it will be much cooler than that average, and in some years it will be much higher than that average. And now the orangey red curve illustrates what happens when there's global warming applied to this particular region. So the whole distribution shifts to the right by a relatively modest amount of around about 1 degree in this particular example. But what I'd like to draw your attention to is the 2 degree mark. So what's the likelihood of exceeding a larger number, 2 degrees in this particular case? And that probability or likelihood is represented by the areas under the graph. So in the old days, the black curve, the area was that tiny little space indicated by area 1 in black. Whereas under the warm planet, that area has now grown to area 2. So that even though we've had relatively modest warming, the size of that area is much, much greater than it used to be. And so it is much, much more likely to exceed 2 degrees with that warming than it was in the old days. So that's the past. Let's now turn to the future. And the future of the planet is going to depend critically upon what humans decide to do with regard to their emissions of greenhouse gases. And what this shows is, and in order to project what that change might be, we use the same mathematical models of the Earth's climate system that I referred to earlier. And if you look at the output from those models, which is depicted here, this shows the globally average temperature of the planet relative to recent decades. So you can see to the left of the plot, there are lots of bumps and wiggles, some of that associated with El Nino, La Nina, some of it associated with volcanic eruptions. But you can also notice that there's been some warming towards the end of the record. That's what the models say, and that's consistent with the observations. But then when you turn to the coloured plots, that's the future. So what it depicts is that there's a very wide range of possibilities for the future for global temperature. And you can see that at the highest level, 4 degrees, 5 degrees around there, that's under business as usual scenarios in which greenhouse gas emissions continue on their merry way, or not so merry way, to grow each year, and we end up with that very, very large warming. At the other extreme, the sort of bluey coloured curves shows what would happen to global temperature if the world acts to very markedly and substantially reduce global emissions of greenhouse gases. Now, of course, the warmer the planet, the greater the impacts are going to be. And so what does this all mean for Australia? Well, some of the key findings have been very neatly summarised in a recent document by the Bureau of Meteorology and CSIRO. So accompanying this global temperature increase, beginning from the top, from the second to top on the left, there will be accompanying sea level rise. And that's going to affect not just globally, but Australia's coastline. And then also the oceans are going to warm, and that's going to be associated with increased ocean acidification. Temperatures will become higher, as we've already mentioned, and that will be associated with more hot days and fewer cold days. And then if we move to the right-hand column, there is also projected, in association with that global warming, a reduction in the total number of tropical cyclones, but a tendency for some of those cyclones to be more intense than they might have typically been in the old days. We also find that in association with global warming that rainfall extremes tend to occur more often. So you tend to get more intense rainfall when it does become intense. And we also find that fire weather in southern and eastern Australia tends to become harsher. And we find that winter and spring rainfall in southern Australia tend to become reduced, and that's associated with an increase in the occurrence of drought and the duration in which we are in drought. So how do we limit these risks? Well, how do we reduce that global warming? So there's two ways. One is through adaptation, which Matt will say something about, and then through things like building codes and limiting urban expansion, for example, through the greater use of early warning and response systems, through public education. And the other major the other major way in which we can reduce these risks is to obviously reduce global greenhouse gas emissions. Both of them are very important. And if we just turn to this last illustration of that, this shows the risks to coral systems in Australasia, the risk of significant change in the composition and structure of coral reef systems. And it shows the present risk, and that little stripe at the top, and that little stripe bar indicates how much you could lower that risk if we were to apply additional adaptation measures that are currently known that aren't currently applied. But then by the time we get to 2030 to 2040, because of the global warming that's going to occur, that risk increases, but adaptation can offset that, but there's still a significant increase. But by the time we get to the end of the 21st century, the risk crucially depends upon what we do with global greenhouse gas emissions. And you can see that if the warming exceeds 4 degrees, then adaptation doesn't move the risk away from being very, very high. So in summary, we've seen that the frequency of hazards affecting Australia vary from year to year and decade to decade, and that the frequency of some and the intensity of some hazards have already increased. And we've seen that there are further increases projected for some, though not all hazards. And finally, we saw that moderating these future risks can be achieved through adaptation and through reducing global emissions of greenhouse gases. Thanks, Jane.
Thank you, Scott.